It's able to record, sir. So I am pausing. So hello guys. So let me welcome you formally. This is Raj Kiran. So we'll start the class just now. Okay. So this is the first lecture on basics of semiconductor physics. Okay. So guys, so during the class I will ask many questions, right? So it should be very interactive, right? So I don't want the class to be only one sided. Okay. It should not be like a passive learner. Okay. So you should keep on asking me, I will keep on asking you, you should respond. So is it okay, all of you guys?
Okay, sir. It's okay. Thank you.
Yeah. So that it will be very interesting. Okay. So the first thing is, you know, so you could see the world is advancing very rapidly. Okay. So can you guys tell me which are the two things that is responsible for this advancement?
Obviously, electronics and this communication.
Yeah, perfect. So the most important is VLSI, or which is nothing but electronics. Second is software, right? So I could see these are the two fields, okay, because of which the world is advancing at a far rapid rate than which you expect, right or not, guys?
Right.
Yeah. So thing is, should be very lucky enough that you are in a branch, okay, because of which the world is progressing. Okay, so you should feel very lucky inside, right? And one more thing, without the advancement of VLSI field, okay, we could not have mobile in your hand, right or not?
Right.
Yeah. So guys, you should be very curious, okay, to know what is so much there inside the semiconductor, okay, because of which there is so much of happening, right? So first thing is, before attending the class, you should be very curious, okay, what are the physics of semiconductor, okay, which makes it so much usable. So like this is not for this class, whichever class you attend, right, you should be coming with some questions in your mind, okay. So from this class, what you will get, right? Like suppose this is my basics of semiconductor, okay. So what is your expectation from this class? Can anyone please tell me what is the thing you are thinking in your mind?
So to reduce the power efficient, to increase the efficiency of existing devices by reducing the size and all those things.
Yeah, fine. So you are absolutely right. But thing is ki, what are the physics of the semiconductor? You need to understand so that you can come up with new devices, new architecture that will reduce the size. Right? This is only one aspect, reduce the size. So also you want reducing the power. Right? So you want to consume less power and get more functionalities. Right or not?
Yes.
Yeah. So thing is, you want to understand the semiconductor physics. After understanding, you have to apply the physics and get new architecture, new kind of devices, okay, which will be power efficient, space efficient, right? Because you see, 10 years down the line, we could not have Android mobile, right? So now we have everything because of in the same size of mobile, you can put many things, right or not?
Right. Right.
Yeah. So the same mobile in 2015, you were getting around 8 GB or 16 GB of memory. Okay. Now people are getting 500 GB also in mobile, right? Because in the same space, the device size is reduced, right or not?
Right. Right.
So, so the size is reduced because there is a lot of research going on in the physics side. Okay. So we will not go to that high level physics, but we should be in a position to understand what is a semiconductor is all about. Fine. So this would be your expectation. Okay. So what are the things that you need to understand, right, in order to convince why the VLSI field is progressing so much. Okay. Hello.
Audible, sir. Audible.
Clear?
Yes, sir. Yes.
So just one thing, whatever I am speaking, is it clear to you or my voice is not coming properly to you?
Yes, sir.
Yes, sir.
Okay.
It's
And
proper.
it is understandable?
Yes, sir.
Sure, sure, sir.
Yeah, means why I am speaking, because I may speak little fast, because that is, but it is okay for you or not?
It's okay, sir. It's normal. It's quite okay.
Okay. So like see, because whenever you are able to, you miss some things, right? You just let me know. Okay. So let me start formally. So guys, this is the syllabus, right, which I have taken from GATE. Okay. So the most important thing in this physics part is this thing, right? So we need to understand what is the intrinsic and extrinsic semiconductor. Okay. So what you will study in this, what is the carrier concentration of intrinsic semiconductor. Okay. So how by doping we can change the concentration or properties of semiconductor. Okay. Then we will understand what is called equilibrium in a semiconductor, right? So this word will come to you very often. Okay. So we need to understand what is this equilibrium. Okay. Then we will see how carriers transport in the semiconductor, right? So what are the speciality of semiconductor, okay, that makes it different from insulator and metal, so that we are using so much the semiconductor only, right? Is it clear, guys? So how the carriers are transported in the semiconductor, that we will study very clearly. Okay. So then using this physics and the carrier transport theory, we will apply this physics and transport into PN junction. Okay.
Yes, sir.
Then if time permits, we also will cover BJT and mass capacitor. Okay, guys?
Okay.
Okay. So the first and foremost thing, what is the course objective? Okay. So from this course, what you will get? Okay. So let me start directly. Suppose I have a diode, right? So all of you know diode, right or not? Right?
Yes, yes.
So thing is, if you apply certain voltage, if you want to plot the current, so if you apply voltage, right, and if you want to plot the current, right, it will be like this. Right or not? Hello?
Yes. Yes, sir.
Yeah. So, but my question is, why the diode behaves in this particular way, right? So, if I apply a voltage, why the current flow in this particular way? Okay. So, this is the objective of the course. Now, nothing but to relate the terminal characteristic, nothing but my current voltage characteristic to the device or material parameter. Okay. So, we want to relate what are the device parameter or what are the thing in the device, so that it is responding in a particular way. Clear, guys?
Please.
Yeah. And also we will understand how ambient condition, right, change the terminal characteristic. Clear? Like suppose this is temperature T1, right? If I go to temperature T2, so suppose this is T2, right? So T2 will be more than T1. Then the IV characteristic of the diode will be like this. Okay. So how this ambient condition, okay, change the property of the device. Okay. That we will understand in the course. Clear? Right?
Clear.
Clear. Okay. Suppose you take a MOSFET. Okay. So in a MOSFET, right, if you plot the current ID, versus VDS. Right? So you know this ID versus VDS will be how much, guys? I don't know. Yes. So what do you think? Why this ID-VD characteristic of my MOSFET is like in this way? Okay. For understanding this characteristic, we need to understand the physics behind the device. Right or not?
Right, sir.
Right. And one more thing I am asking. Have you ever thought ki why the characteristic ID-VD characteristic is like this? Like means so first this one or the first MOSFET? Which one? Which is first, which is second? Like what I'm telling, first the MOSFET is derived, then the IV characteristic have come, or the first IV characteristic, then the MOSFET have derived. Which one is you are thinking? Like getting my question? My question is, first people have developed MOSFET, then they got the IV characteristic like this, or they want the IV characteristic like this, that's why they developed the MOSFET. But which one is right you are thinking? So I am repeating my question. First,
Okay.
people want the current voltage characteristic of MOSFET like this. That's why they develop MOSFET, or they developed MOSFET, then this current voltage characteristic have come. Which one you are thinking? Right.
I think the based on the diagram, they have thought about this device so they can control like this. I don't know, but it's a guess.
Yeah. So any other persons can? Please see, you first free, completely free, okay, and talk to me. Then it will be very good to you. Okay. Guys, whatever you think, there's nothing to shame about. Just whatever you're thinking, just share me so that you will go accordingly, right? So my question is, first the IV characteristic have come, then the MOSFET have come, or the first MOSFET have come, then we have derived the IV characteristic. Which one are you thinking?
So I think based on the
Characteristics come after that we fabricate the device.
Perfect. May I know who is this answer? Who told this answer?
Dr. Ali Khan.
Yeah, perfect. See, you have made a very nice point. Okay, you see, if I want my ID VDS characteristic like this, okay, so just simple question: can someone tell me why I want my ID VD characteristic like this? Can anyone tell me? This is a very interesting question. Why at all you want this characteristic like this? See, the diode you understand, you want like this because you want as a rectifier, right? So first people want a rectifier, right? Then they come to physics, they sit in the ground, then they thought of how to arrange the semiconductor so that it will give me a rectified characteristic. Clear, guys? So first people want how to rectify a signal, right or not? So in order to meet this criteria, rectification, they have come up with the diode, right? So similarly, this characteristic, why people wanted?
चाहते हैं कि हमारा जो डिवाइस है वो एक करंट सोर्स की तरह काम करे because ID is constant.
Okay, fine. So okay, this is one answer. Any other person please? Yes, please respond. It will be good for you. See, the more you respond, right? See, tomorrow if you go to interview, right? Definitely they are going to ask questions like this. You should be very free.
To have a two states such that first the current will be limited and then it will become constant at some point.
Okay, good. See, you should answer something. Okay, then if I tell this answer is wrong, right? Then you will rectify, right? Okay, what you are thinking, the thinking process is wrong, right? So this will help you a lot to learn the thing. Okay, so thing is, why this ID characteristic is very important, right? You will understand in analog circuit only when we are in this region, right? This is called saturation region in MOSFET, right? Only when my device is operating in this region, it will act as amplifier, right? So first people want to amplify the signal, right? In a communication, if you see the signal you receive is very low, right? So first people want to amplify it, right? So then they come this IDPD characteristic, they understand that if my characteristic is like this, it will act as an amplifier. Okay, so you take this statement, you understand. In the coming class, you let me know why at all when my IDPD characteristic is like this, it will act as amplifier. Okay, so this is homework question to you. Okay, you note it down. You let me know in the next class. Okay, why the characteristic should be, why the MOSFET should be in saturation to act as a amplifier. Is the question is clear?
One more time, sir.
So my question is, why my MOSFET need to be operated in this region, which is called saturation, in order to behave as a amplifier.
Okay.
Clear? All of you clear? The question is clear?
Yes, sir.
Okay. So you take this question, you think, come up with the next class. I'll ask you and you should answer the question. Okay?
Sure.
Okay. So thing is, we'll understand this is the characteristic required for the amplification. Okay. Then people have gone, set, come up with device MOSFET. Right? So this MOSFET is giving this characteristic. Okay. So you may be amazed to know in a BJT, right? Which is in a BJT. Okay. This is my collector. This is my base. This is my emitter. Right. So in this also, if you see the IC BC characteristic will be like this only. Right or not? Right or not? Hello? Hello, am I audible?
Yes, sir.
Yes, sir. It's all.
Yeah. So in a BJT also, if you see the output characteristic is similar to MOSFET only, right or not? Okay. So there is no surprise, there is no coincidence. People want the characteristic like this so that you can use this device as an amplifier. Clear?
Clear.
Yeah. And suppose tomorrow you come with some new device, right? And you want as an amplifier. Okay. Definitely. Suppose your name is, what is your name? Suppose your name is suppose Siri. Okay, so Siri have developed one new device to make as amplifier. Okay, then also the Siri device also, right? The Siri device also should be like give like this, the IV characteristic, correct? Then only this will act as amplifier. Okay, so tomorrow you come up with, suppose see in 2005 onward, right? People were discussing so much of BJT, right? Now people are studying so much of MOSFET. Okay, so device is changed, but the characteristic is similar or not, right? Similar. So tomorrow there will be new MOSFET will come, FinFET. There are many things is coming. Okay, but the characteristic should be similar. Okay, to act as a amplifier. Okay, so this is a homework question. You let me know, otherwise I will explain you. Okay.
Okay.
Okay. So in this class, we will understand how to derive this characteristic from the physics. Okay, and also how to get this rectification from the physics. Okay, we will not use the diode as a circuit, but we will understand how this particular characteristic is coming. Clear? This is the objective of the course. At the end of the course, you will be understanding how this characteristic is coming, what is the physics behind the characteristic. Clear? Okay. So in this course, Guys, main aim is to relate the terminal characteristic, nothing but the current voltage characteristic, or small signal characteristic, nothing but you have to find out the gain, bandwidth. Okay, these all are the small signal characteristic. So we want to relate the DC characteristic or AC characteristic of the device to its material parameters. What are the material parameters? Like how is the geometry? Right? If you take a big diode, the current will be more, right or not? So how geometry of a device is affecting the characteristic, right? Second, we will understand how doping. Doping is nothing but intentionally we are adding some impurity, right, in order to change the conductivity, right or not, guys?
Right, sir.
Right, and we will understand how doping is affecting the characteristic, right? Next, we will understand how if you take silicon or germanium, right? So their band gap is different, right? So how this band gap is affecting your DC and AC characteristic, right? Then you will understand mobility. What is called mobility? So in different semiconductor, in different doping, how the mobility is changing. Okay, so mobility is changing means my DC current voltage characteristic is changing. Mobility is linked to current, right? So higher the mobility, higher is the current, right? Similarly, we will understand how lifetime of the carrier is important. Okay, so then also we will relate the ambient condition, right? Nothing but temperature, right? So if my device is under high temperature, right, how the current voltage characteristic should be, right? Or if a semiconductor is under illumination, right, with light or some other energy, right? So if a semiconductor is under the influence of light or something, right, how it will behave, right? So we will you guys, hello,
Sir, voice is cracking.
okay. So shall I repeat?
Yes, sir. Yes, sir.
Okay, so let me repeat. Okay, it's very good that you have pointed out. So what I want, right, how geometry of a device, right, is affecting the current voltage characteristic. Clear, guys, all of you?
Clear, clear.
Yeah. Suppose
It's clear, sir.
suppose you take a big transistor or big diode, right? So how the geometry is affecting my current? Okay. So doping means intentionally to a semiconductor we are adding impurity, right? So the impurity will change the conductivity, right? So how different dopings are intentionally used, how different impurities are intentionally introduced in the semiconductor to change the property of a semiconductor, right? That we will understand. Clear, guys?
Clear, clear.
Clear. And also we'll understand what is energy gap. What is this actually? Okay. So in physically, what is the meaning of energy gap? So can anyone tell me what do you mean by energy gap?
Difference between the conduction band and valence band.
Yeah. So physically, what do you mean by that? How it come about in the semiconductor? Why it is not there in metal? Okay. See, whenever I am speaking something, right, you should keep asking question to yourself. Okay. It's not that every time I only ask question to you. You should ask questions. You should be very curious to know what is happening. Okay. So what is mobility? So you should understand. So if I tell some word, right? So suppose if I tell mobility, okay, in your mind you should imagine what is I am talking about. What is the thing that is going to happen? Okay. So if you imagine, right, you need not to mock up anything in the subject. Clear?
Clear, sir. Clear.
Clear. So I will try to give you a very good virtualization of how the semiconductor behaves. Okay. So you need not to mock up anything in the exam for the exam. Okay.
Okay, sir.
Okay. So one more thing, what is called ambient condition? Like how the surrounding of a semiconductor, right? How the surrounding of a semiconductor affecting the property, right? Suppose if a semiconductor is in higher temperature, right? So if my semiconductor is in higher temperature, how it behaves? Clear?
Clear, clear.
Clear. So now whatever I have spoken, is it clear to all of you or not?
Clear, sir.
Guys, is there anyone who is not getting what I'm telling? Hello?
Sir, what is ambient temperature? Ambient temperature.
Ambient means surrounding temperature. Like suppose your diode is in Himalaya. In Himalaya, temperature is 40 minus 40 degree, right? Suppose you are in Hyderabad, it's 30 degree, right? So the device will behave differently if it is in Himalaya or in Hyderabad. Clear? Hello?
Yes, sir, clear.
Yeah. So see, suppose you are designing one IC. Okay. So it is supposed to work everywhere, right? Not like you can tell ki I am having this IC. You use it only in India, not in Europe. That is okay.
Sir. No, sir.
Hello? No.
No,
So
sir.
we have to design the device such a way that it should work almost all the conditions, right? That we have to ensure, right? So if you understand what are the properties of semiconductor that is affecting my current voltage characteristic, then you will design accordingly, right or not?
Right.
Right. So the understanding is very important, right? So I think the objective is very clear to all of you. What you are going to do.
Yes, sir.
Okay. So guys, again I'm telling, if whatever I'm speaking, is it clear to you or my voice is not coming properly to you?
Yes, sir. Clear.
Clear.
And my pace also okay, pace?
Yes, sir, page is also okay.
Okay, fine. Okay, so we'll go next. So my question is, why semiconductor is used so extensively comparing to metal and insulator? Right? My question is, why semiconductor? You should ask yourself, okay, why at all semiconductor, right? Why at all semiconductor? Why not metal? Why not insulator? Okay, can you tell me, guys, why at all we will use semiconductor?
It acts like both conductor and
Yeah, but question is why? Suppose if it acts like both insulator and conductor, but why you want this?
We need a switching device so that we can control it.
Perfect. This is perfect answer. Okay. So the controllability is there in the semiconductor. Right? You can control what you can control. Okay. You can control the conductivity. Right? You can control the concentration. Right? You can control the basic current voltage characteristic. Right? So because of its controllability, okay, this is used everywhere. Clear, guys?
Yes.
Yeah. So in order to use the semiconductor, what you need to understand, what is electrons and holes. Okay. Why a vacancy in a semiconductor? Why a hole takes part in the current? Right. So what is a hole? What is electron? Right. Why? How it is generated? Okay. So at equilibrium, what is the concentration of electrons and holes? Okay. So how the electron and holes are transported? Like suppose if you apply voltage, okay, how the current will flow? Okay. And also we have to understand, if it is under the influence of suppose light, okay, how it will perform. Okay. So all these things if you understand, right, you can use the device in your circuit. Clear, guys?
Clear.
Clear. So till now I am just introducing the subject to you. Okay. So now we will start the subject. Okay.
Okay.
Okay. So the first chapter is how to get the carrier concentration in intrinsic semiconductor. Okay. So first thing is, whenever I am speaking, right, you have to think in your mind what is intrinsic, right? What is concentration? Okay. So you should keep asking yourself. Okay, then only it will be very useful for you. Okay, so we will try to analyze what is a intrinsic semiconductor. Okay, so also we will try to get a expression for the number of carriers per centimeter cube. Okay, so this is the meaning of carrier concentration. Okay, like number of electrons, right? Electron or of electron per centimeter cube of the semiconductor. Okay, so how to get a expression for this? Okay, or on what factor this concentration depends on? Getting, guys?
Yes, sir.
Yeah, and yeah, so what are different type of semiconductor? Okay, there is something called P type, N type. Okay, what are these? How it come about? Okay, then we will discuss what do you mean by a semiconductor in equilibrium. Okay, so almost all the chapter we will study, you will see this term, the conductor in equilibrium. Okay, what do you mean by equilibrium? Okay, what do you mean by when I say my semiconductor is in steady state? Okay, so what is the meaning of steady state? Okay, so then we will understand what is called a intrinsic semiconductor. Okay, so then in order to find the concentration of electron and hole per cm3, right? There are two models. One is called bond model. Bond model means it will explain you very qualitatively. Okay, not quantitative. Right? It will explain you qualitatively how much should be the concentration. Okay, so you should get a feel of how the electrons are generated. Okay, so this is nothing but bond model. Okay, this band model will give you a very accurate number. Like suppose you ask me what is the concentration of electron at temperature T is equal to 300 Kelvin. Okay, then this band model will give you a exact number. Okay, so this is just for mathematical calculation. This is for your understanding bond model. Right? Right, guys? Yeah, and then we will understand how different. What is the different way the carriers, nothing but electron and holes, are generated in semiconductor. Okay, and means what is the ways of generating carrier? Okay, then we will understand what is a hole. Okay, how this come about? How a hole, nothing but vacancy space, helping you in conduction. Okay, have you ever thought of this one? Yes.
Yes, sir. Yes, sir.
Okay. So let me start. So guys, there are two types of semiconductor. Okay, one is called simple, another is called compound. Okay, simple means a semiconductor made up of only one element. Okay, compound means it is mixing of more than one element, right? Gallium arsenide, indium phosphide, gallium indium arsenide. Okay, so it is mixing up all the different elements. Okay, also the semiconductor can be pure. Pure means, guys, it is ideal, no impact, no impurity, and no defect. It's perfect semiconductor, right? It's like all the atoms, all the elements, each arranged in a perfect way. There is no deviation in the semiconductor, in the crystal. Clear? So this is pure. Pure means it's completely ideal, right? Which is not possible in real world. Right or not?
Right, sir.
What do you mean by intrinsic? Intrinsic means, see, words are very important. Okay, so it's, when I call my semiconductor intrinsic, it may not be totally pure, right?
Doping.
Hello? Tell me.
Doping.
No, brother. Doping will come in extrinsic. Okay.
Yeah, extrinsic, sir. Yes.
So in intrinsic, what is the difference between pure and intrinsic? Pure means no impurity, no defect. It's completely perfect. All atoms are arranged in a particular way. There is no deviation. It's like building a model in computer. Okay. So in real life, definitely when you are getting a wafer or semiconductor, it have some impurities, right or not? Right?
Right, sir.
Yeah. So a intrinsic semiconductor is not totally pure. Okay, it has some impurities, but the concentration of electron and holes of this intrinsic semiconductor is same as that of pure semiconductor. Getting this meaning? See, what happens even if impurities are present in the intrinsic semiconductor, right? Even if there are impurities in intrinsic semiconductor, okay, but the concentration of electron and hole is same as that of pure semiconductor. Okay, suppose you take a pure one. Okay, this is a pure one. Okay, you take a intrinsic one. Okay, so if you see a T is equal to 300K. Okay, if you calculate the electron or hole concentration in pure and intrinsic will be same. Getting guys? And what is the effect of impurity in intrinsic semiconductor? Impurities are there, but thing is the effect of one impurity cancelling the effect of other impurity. What do you mean by? There are some impurity which will try to increase the electron concentration, and also there are some impurities which will try to decrease the electron concentration. So in effect, the net concentration will be same as pure semiconductor. Clear, guys?
Clear.
All of you clear? What is the difference between pure and intrinsic?
Yes, sir.
Yeah. So in intrinsic, even though impurities are there, there are different types of impurity. One type of impurity will try to increase the electron concentration, and another type of impurity will try to decrease the concentration. So in effect, the concentration is equal to same as pure semiconductor. Clear? Yes. Yeah. And as our friend told, what is the extrinsic semiconductor? Whenever a intrinsic semiconductor is doped, okay, we will get extrinsic semiconductor. Means it has defect and impurity, and these impurities are intentional. Okay, but in this intrinsic semiconductor, the impurities are not intentional. Okay, impurity non-intentional. Clear, guys? All of you clear? So in extrinsic semiconductor, we are adding impurity intentionally to change the concentration. Clear?
Clear.
Clear. So now you got the idea of what is pure, what is intrinsic, and what is extrinsic.
Yes.
Okay. So these impurities are intentionally we are adding, okay, in the semiconductor to change the conductivity. Okay. Okay. So guys, this is a question. Okay, for all of you. Silicon can be a intrinsic semiconductor, extrinsic semiconductor, simple semiconductor, or all. Which is the answer, right? Right, guys. There is a question only on the first. This is my first
All.
slide.
All, sir.
Okay.
All.
Yeah, you see this, na? You see, silicon can be simple. Also, it can be pure, intrinsic, or extrinsic. Okay, it can be, right? If I dope silicon, it will become extrinsic. Right or not?
Sir, yes.
Yeah. So see, this question looks confusing if you do not understand this concept. Right or not? So my thing is, guys, first understand the things very clearly. Okay. Then answering in the exam will be very fun. Okay. If you understand things properly, you can easily answer the question in the exam. Right or not?
Right.
Right. Okay. Okay. So this is a very important concept. What do you mean by thermal equilibrium? Okay. So let me explain you what is thermal equilibrium. Okay, first let me read the statement. Okay, a semiconductor is said to be in equilibrium with its surrounding. It's very important. Okay, if for any process that may be going on between the semiconductor and surrounding, there is a inverse process going on at the same rate. Okay, so let me explain pictorially. Suppose this is my semiconductor. Okay, what do you mean by thermal equilibrium? Like if there is any process going on between semiconductor and surrounding, right? Okay, so okay, suppose there are 10 electrons going from 1 to 2. Okay, 2. Okay, suppose there are 10 electrons, okay, going per second, okay, from 1 to 2, then there should be exactly 10 electrons should come from 2 to 1 at the same rate in 1 second. Clear? So for every process, that is, there is a inverse process. Okay, if there is a carrier moving from 1 to 2, then definitely there should be a carrier moving from 2 to 1 at the same rate. Clear? That is called thermal equilibrium. Let's, is it clear to all of you?
Yes, sir.
Yes. Also see, also suppose in the semiconductor there are 2 points. Okay, there is a point A point B. Okay, suppose point A to B, okay, 100 electrons per second are moving. Okay, then exactly 100 electrons should move from B to A, exactly 100 electrons per second. Right? So for any process, there should be a inverse process at the same rate. Clear, guys?
Please.
Clear. Also one more thing. Suppose out of this here, out of 10 electrons, right, 5 are having energy E1 and 4 are having energy E2 and 1 is having energy E3. Okay. Similarly, from 2 to 1, 1 to 2 also, same. 5 electron will have energy E1, 4 will have energy E2, 1 will have energy E3. Like at every level, there should be a reverse process. Clear, guys?
Clear. Clear.
Clear. So this is called detail balance. Okay, this is called principle of detail balance. So you go to any detail you want, there should be a inverse process at the same rate. Okay. So my next question is how to tell what are the see? Did you understand? Right or not? Hello.
Yes, sir. Yes,
Yes.
sir.
So suppose I will ask you like what are the conditions that my semiconductor will be in equilibrium. Okay. So this is your qualitative understanding. You understand qualitatively. This is the process. Okay. This is the thing happening. You understand qualitatively. Suppose I want to list down some conditions when it will be in equilibrium. Okay. So the first condition will be there should be no external excitation other than temperature. Okay. So a semiconductor is said to be in equilibrium if the first condition is there should not be any external excitation other than temperature. Clear, guys?
Clear.
Clear. And second condition should be there is no net motion of charge and energy. Okay, there is no net motion. See, there is a motion, right? There is a motion of carrier. Okay, but if you see any cross section, there is no net motion because here A to B 100 electrons per second, B to A 100 electrons per second. That means if you see this cross section, any cross section, net is equal to 0. Right or not?
Yes, sir.
Right.
Right. So thing is there is no net motion of charge carrier. There is that doesn't mean that is it meaning that ki charge or energy is not moving, there is no motion. Can I say like that? When a semiconductor is in equilibrium, can I say the charge or energy is not moving? Can I say like that?
Yes, sir.
No. See, this charge is moving, right? Here, electron is moving from A to B. And how we are telling it's not moving? It is moving, but there is no net motion. Okay, if you see any cross section, right? Any cross section, there is no net motion, right? There is a motion, but the meaning of net motion will be means one type of motion is cancelled by the other type of motion. But you cannot say the charges are at rest; they are moving so fast, but net is equal to 0, right or not?
Right, sir, right.
So all of you understand the charge or energy is moving in a they are in motion, okay, but net is equal to 0. That is the meaning of equilibrium. Equilibrium doesn't mean that they are in rest, they are sitting silently in the semiconductor. Guys, are you getting this point?
Yes, sir.
Yes. So let's take some question. Okay, suppose I have a semiconductor. Okay, so I am illuminating with light. Okay, so my question is, if this semiconductor in equilibrium or non-equilibrium? Guys, quick.
Non-equilibrium.
Non-equilibrium, sir, because
Yeah.
quasi-Fermi level will be exist in this case.
What? Quasi-Fermi level. What is quasi-Fermi level, brother?
Sir, excess carrier will be generated na, by the light illumination.
Yeah. So you are going little ahead. Okay, that's very good that you are going ahead. But thing is, we have not reached that point. Okay, only thing is we have studied these two things. Okay, first condition is no external excitation. But unfortunately, this is external excitation, right? This condition is not meeting. Straightforward. So you have to check two conditions. First condition is no external excitation. But here I am putting light. This is external. Then that's why it's not in equilibrium, right? And whatever you spoken, that is right. Guys, is it clear?
Clear, sir.
Clear. Okay. So suppose there is a semiconductor. Okay. One end is a temperature T1, another end is temperature T2. Okay. And T1 is greater than T2. Okay. So can you tell me if this is in equilibrium or non-equilibrium?
Non-equilibrium, sir.
Okay, good. But why it is non-equilibrium?
Two different temperatures, sir.
Okay. Then what will happen?
If one is greater, one is greater, another one is lesser. Charge carriation will be different, no, sir.
Very good. Perfect. So first criteria is no external excitation other than temperature. This is meeting, right? Because there is only temperature only, right? There is no other external excitation than temperature, right? The first condition is meeting or not meeting. Guys, for this second question, the first criteria is meeting or not meeting. This one.
It is meeting.
Meeting. But the second criteria, no net motion. But since the temperature is more here, temperature is less here, the heat energy will move from 1 to 2, right or not? So there is a motion of charge and energy from 1 to 2. Clear? So, but according to the second condition, there should not be no net motion, right? So this is not meeting, right or not? Because it is higher temperature, the heat energy, right, will move from 1 to 2, right or not?
Right.
Right. So since there is a net motion of energy from 1 to 2, so it is not in equilibrium. Okay. Third condition. So guys, you should respond so that I will be also very active. Okay. Suppose I have a voltage supply. Okay. So tell me whether this is in equilibrium or non-equilibrium.
Also non-equilibrium, sir.
Because one is at 0 volt and one is at V volts.
Okay. So what?
There will be net motion, won't be 0.
But why we are jumping to second? First thing is first criteria is what? There should not be no external excitation.
Externals
Putting
also.
external electric field.
Yeah, yes, sir.
Electric field. So thing is why you should go for step by step. Okay. So
Okay, sir.
since first criteria is not meeting, I need not go to second criteria at all. Right or not?
Yes,
so
sir.
there is external electric field. So it's not in equilibrium. Clear? So
Yes, sir.
this equilibrium we will come across thousands of time in the course. Okay, so that's why I have given some examples to make you understand what is the equilibrium. Okay.
Okay.
Okay. So then what is steady state, guys? Steady state. So you tell me. It means all process are constant as a function of time. Okay. It is not necessarily that for all process there is a inverse process. Clear? So steady state means suppose from point 1 to point 2. Okay. 100 electrons per second moving. Okay. So but this 100 electron per second should not vary, right? So it should move at the constant rate. It's not like on first second, in first second 100 moved, second 150 moved. Okay, then it is not in steady state. Okay, steady state means there should be 100 electron, it should be constant. So the process should be constant. So if it is 100, it should be 100 for every time. Okay, because to time it should be constant. Okay, and it does not mean that if there is a 100 electron from 1 to 2, no guarantee that, or no guarantee that there will be 100 from 2 to 1. Not guaranteed. Clear?
Clear.
And whatever happening, that should be constant with respect to time. Okay?
Okay.
Okay. So can I ask you one question? Okay. If a semiconductor is in equilibrium, then it will definitely in steady state. Is this statement right or wrong?
Yeah, it is
Huh?
true, sir.
True, because we know for equilibrium, for every process there is equal and opposite process. Okay, at the same rate, right? This you see, same rate. I don't know. I mentioned. Okay, so you see, sometimes in every definition, right, you have to understand word by word. Okay, you see. So whenever a semiconductor is in equilibrium, so then it will definitely in steady state. So I can say, suppose this is a steady state, then equilibrium is a subset of this one, right? I don't know.
Right, sir.
And whenever a semiconductor is in steady state, can you guarantee it is in equilibrium? So if a semiconductor is in steady state, can you guarantee that it is in equilibrium?
No, sir.
No, because the reverse process is not guaranteed, right?
Yes.
Not necessary, sir.
Pardon me? So when a semiconductor is in steady state, it may or may not be in equilibrium, right? If there is a reverse process, then it is in equilibrium. Otherwise, not in equilibrium, right or not?
Right.
Yes, sir.
Right. So I am making one strong statement. Whenever a equilibrium is there, then definitely it is in steady state. But the reverse is not true, right?
Right.
Clear, na? Okay. So this is very important point. You just have a view on this. Okay. So there is a question for you. When a semiconductor is in steady state, then it is definitely in equilibrium. When a semiconductor is in equilibrium, then it is definitely in steady state. When a semiconductor is in equilibrium, then it may or may not be in steady state. Which one is right?
B only.
B, na? Guys, which one is right?
B, sir.
B only.
B, right? So B. That's very good. Clear, guys? All of you clear?
Yes, sir.
Now, with this background, okay, we'll start what is called bond model of a intrinsic semiconductor. Okay. So, what is this actually? We want to understand qualitatively what is the electron and hole concentration in semiconductor. Okay. So, this model gives a qualitative understanding of why there are electrons and holes in semiconductor, right? So from this model you will appreciate why there are electrons and holes, right? It will try to explain you why the temperature coefficient of resistance of semiconductor is negative, right? Like nothing but if I increase temperature, why the current is increasing? I don't know, guys. In a semiconductor, if I increase temperature, then the resistance decreases or the current increases. That is right or not?
Right, sir.
Right. So we will understand why it is happening like this. Okay. Next we will understand. It will try to give a rough idea of what is the concentration of charge carrier. Okay. Also it will, but it is not helpful for getting accurate calculation. Okay. Suppose I ask you what is the electron concentration at T is equal to 500 K. It will not give you. Clear, guys? Hello? Is it clear to all of you?
Yes, sir.
Okay. So what is a bond model, right? So if you see silicon, right? Silicon, okay? Silicon, if you see the two-dimensional structure of silicon, right? So each silicon is bonded to four other silicon, right, by a covalent bond. That is called covalent bond. So nothing but coming with sharing of electrons. Is it clear? Right or not? So if you see semiconductor, each silicon atom is bonded to four other silicon atoms. Is it clear to all of you? We see this silicon 1, 2, 3, 4. So for every silicon atom is bonded to four other silicon atoms. Is the statement right to all of you?
Right, sir.
Guys, you respond quickly so that we will go quickly. So, hello?
Hello, sir.
My question is, a silicon in a silicon crystal, right? Each silicon is bonded to four other silicon atoms. Okay, so this is the two-dimensional picture of a silicon crystal. Is it clear? So here you see there is a four bond to each silicon atom, right? So, and if you see at T is equal to 0, right? T is equal to 0, all the bonds are bonded. So all the electrons are bonded. No electron is free. Okay. So at T is equal to 0, right? Even though there are electrons, right? They are bonded by a bond. Okay. They are not free. So at T is equal to 0, even though there are electrons, since they are bonded, they are not available for conduction. Okay. That's why it behaves like an insulator. Clear, guys, all of you?
Clear, sir.
Clear. So if you see the more easy picture, I can say even more simplistic picture of a silicon crystal. Okay, so each junction, if you see in this net, each junction is a silicon atom, right? So if you see each junction, right, there are four bonds, right? Any junction if you see, there are four bonds, right? Guys, is it clear to all of you? And junction is nothing but a silicon atom.
So,
Guys,
what's this diagram about?
the diagram is about two-dimensional presentation of silicon crystal. Okay, so here what I'm telling, in this I have showed you, each silicon is bonded to four other silicon. Right? Here is like nothing but each junction is a atom. Right? Each junction is a atom. This is silicon. Each junction. Okay. So this is nothing but bond. This is a bond, right? These are the silicon atoms. These are the. This is a simplistic view of two-dimensional model of silicon atom. Clear?
Clear.
Clear. So what I am meaning from this is each atom is bonded to 4 other silicon atom by a bond. This is a bond. Okay, this is a bond. Clear? And
Clear.
all the bond is occupied. All the bond is bonded. So no electron is free at t is equal to 0. Clear? So since there is no free electron, even if you apply a voltage, there is no current, there is no motion of electron. Clear?
Clear.
Clear. That's why at t is equal to 0, it behaves like a insulator. Clear? Okay. So now you see what will happen at t greater than 0. Okay. So at t greater than 0, what will happen? You know, when I raise the temperature, right? What will happen? The silicon atoms will vibrate. I don't know.
Right.
Right. So when I go on increasing the temperature, right, the silicon atom will vibrate like this. Level vibrate. Okay, it will vibrate like this. Right. So because of the thermal energy, the silicon atom will vibrate. So when it will vibrate, right? So this vibration will pass to all the atoms also, right? So all atoms will vibrate, and that will generate an elastic wave. It's like there is elastic 0.1, 0.2, 1, 2. So okay, if this atom will vibrate, right? This will vibrate. There will be a wave, right? I don't know, guys.
Right.
Right. So is it clear to all of you? Again, I am explaining it. Suppose there is elastic, okay, by 2 ball, 1 or 2. Okay. Suppose this 2 second atom will vibrate like this. It will vibrate. When it will vibrate, okay, it will pass the elastic wave to ball 1 also, na? Right or not?
Yes, sir.
Right. So at t greater than 0, all atom will vibrate. Okay, that will generate elastic wave, and that will pass to all different atoms. Clear? Statement is clear. So at t greater than 0, silicon atom will vibrate because of thermal energy. So the bond will vibrate, and it will send energy to every atom. Because see, if this will vibrate, it will send energy to this, everyone. Right? It's like a net. Right? So if you see, if it will vibrate, right? This energy will move to all other atoms, right or not? Clear, guys? So if suppose this will vibrate, then the vibration energy will pass to all other atoms or not?
Pass. Surely pass.
Surely pass, right? It's like suppose you throw a what do you call if you throw a mud to a pond, okay? So if you put in one place, right, the wave will pass to all over the pond or not? So suppose there is a steel pond is very steel, okay? You just throw a means some stick, okay? Then whatever wave will generate, it will pass to all over the surface, right or not?
Right, sir.
Right. Similarly, at t greater than 0, silicon will vibrate, and this will generate elastic wave. Okay, called phonons. Okay, and whenever an atom vibrates, right? Whenever an atom vibrates, you see silicon atom. If you see, okay, any atom if you see, at the center we have a nucleus, right? And the electrons are moving around the nucleus. Right or not, guys? In any atom, okay. So when it vibrates, right? When it vibrates, the center of mass of positive charge will be displaced from the negative charge. Center of mass. Okay. So there is nothing but a dipole. Okay. So a vibrating atom will behave like a vibrating dipole. Is it clear to all of you?
Yes, sir.
Yeah. Because when a atom vibrates, the electron and the nucleus will not vibrate coincidentally. So there will be a misplace between the. There will be a center of mass of this electron will be little bit varied from the center mass of the holes, the positive charges, right? So what I am telling, when the atom will vibrate, the center mass of the electron will displace from the center mass of the nucleus. Okay, so there will be a separation between the negative and positive charge, so it will behave like a dipole. Okay, so what I am telling, a vibrating atom behave like a dipole. Atom behave like a dipole. Is it clear to all of you?
Yes.
Yeah. So at t greater than 0, I am summarizing. The atom will vibrate. It will generate elastic wave called photon. It will generate vibrating dipole. Okay. The vibrating dipole will generate photons. Okay. Nothing but electromagnetic wave. Okay. So at t greater than 0, in my semiconductor, I have phonons. I have photons. Photons is nothing but vibrating atom generated dipole, and when a dipole vibrates, it generates photons. Okay, so at t greater than 0, I have phonons, nothing but elastic waves, and photons in the semiconductor. Okay, so what happens when a silicon atom get enough energy, then the bond energy, right? A bond will break. Okay, suppose it get energy from phonons and photons, right? If this atom get enough energy, then the bond energy, right? This bond will break, this electron will emit, right? Clear, guys? So whenever the silicon atom will get enough energy, then the bond energy, right? Suppose the bond energy in silicon is nothing but 1.1 electron volt, right? So if it gets more than this one, this bond will break and the electron will emanate. Okay, emanate. So similarly, more number of bonds will break if they receive energy of 1.12 electron volt. So at t greater than 0, since many bonds are broken, I have electrons which are free to move. Right? So I will have electron concentration at t greater than 0. Is it clear to all of you? Yes. Hello.
Sir, I was just thinking like when you told about the vibrating atom, like, it's like a dipole and it gives photons. That means every time photon is liberated or something.
Yeah. See, it liberated constantly. Okay. See, the silicon atom will get energy from any, all the places, like this will give energy, this will give energy, anyone can give energy to this one, right? So anyone can give energy to this one, right? So it will receive energy from phonons and photons continuously, okay? But when it will receive energy altogether 1.12 electron volt, nothing but my bond energy, the bond will break. Otherwise, the bond will not break. Clear?
Okay.
So see, suppose the temperature T is equal to very less. Okay, even if it receives, suppose T is equal to suppose you take T is equal to you take suppose 15 kilovolt Kelvin. T is equal to you take suppose 200 Kelvin. Okay, so at 15 Kelvin also there will be some vibration, but the energy is not sufficient to break the bond. And how will you will get an electron? Getting? So phonons and photons will be there every time whenever t greater than 0. But a bond should be broken only if they get necessary energy. Clear?
Clear.
Clear. So all of you clear, guys? Saik, Surjit, Arya?
Yes, sir.
It is very much clear or some doubt is there?
Clear, sir.
Yes. So now you understand at t greater than 0, okay, I have electrons. Okay. So at t greater than 0, I have electrons in the semiconductor. Okay. So whenever the electron, right, leave this space, bond will be empty, right? I don't know. Earlier the bond is between electron to electron. Whenever the electron will leave, I have a vacancy, right or not? Hello?
Yes, sir. Yes.
See, whichever bond broken, right? Suppose this bond is broke. So the electron will move, then leaving behind an empty space. Clear?
Clear.
So this empty space is called hole. Okay, suppose this bond broke. This bond broke. This bond broke. Electron will emanate. Okay, leaving behind a hole. You see, suppose this bond broke, electron will emit, leaving behind this vacancy space called hole. Here, so I can write the statement: electron and hole always unit in pair. Right? If the statement is clear to all of you. See, whenever a bond is broken, electron is moving away, leaving behind a empty space. That is called hole. So, in a intrinsic semiconductor, at t greater than 0, always the electron and hole generated in pair. Is it clear to all of you?
Clear, sir.
Clear.
Yes, sir.
Clear. So now in your mind, you might be thinking, suppose the electron and holes are generated, right? Suppose I have a semiconductor, okay, at some temperature greater than 0, right? So this electron and holes are generated, right? So if it is generated, right, then at any temperature, right, the concentration will go on increasing. Is it right or not? Suppose it go on generating, then the concentration will go on increasing or not?
Yes, sir.
Yes, but for an intrinsic semiconductor on equilibrium, at equilibrium, suppose this is in equilibrium, okay, the concentration of electron and hole are constant at any temperature. Suppose if I increase temperature, then it will increase. So at a particular temperature, it should be constant. Suppose at T is equal to T1, electron is equal to hole concentration is equal to 10 power of 12 for cm3. If I go to T is equal to T2 greater than T1, okay, then E and hole maybe become 10 power 13. Right? As long as I am at T1, it will maintain at 10 by 12 centimeter per centimeter cube. Right? If I go to T2, then it will increase to 10 by 13. Right? So as long as I am in a particular temperature, the concentration remain constant. Guys, is the statement clear to all of you?
Clear, sir.
Clear. And why? So my question is how it will remain constant? Like suppose I am at T equal to T1. Why the electron hole concentration in a intrinsic semiconductor at a particular temperature remains constant? This statement is clear to all of you? My question is how the electron and hole concentration in a semiconductor at a particular temperature remains constant. If I increase temperature, it will increase, but for a particular temperature, it will remain constant. Is it clear?
Clear, sir.
Clear. But how it happens? Okay, let us discuss how it happens. Okay, so at t greater than 0, right, the electron hole pair generate. Okay, so but how the concentration remain constant means whenever they are generating, right, in some other place there is recombination going on. Okay, so since at a particular temperature the generation rate equal to recombination rate, so the concentration remain constant. Clear? Guys, how the balance happening? Okay, so whenever there is generation at a temperature T constant, then there should be a recombination. Okay, suppose here there are a lot of generation, somewhere here may be recombination. Okay, so in totally the recombination is balanced by the generation. That's why the concentration is remaining constant at temperature T equal to constant. Clear? Hello? Hello?
Yes, sir.
So you tell me, is it clear or some doubt is there in this statement?
Sir, clear.
Everyone is clear, na?
Yes, sir.
Okay. So how the balance happens? Okay. So for every generation in equilibrium, there is a corresponding recombination. Okay. Suppose there is generation because of photon. So I showed you that generation because of photon. Okay. Then some other place there will be recombination because of that is called see. Suppose light fall in an atom. Okay. Generated electron and suppose light fall in an atom generated electron and hole. Right? This is called photogeneration. Right? What is the corresponding recombination? It will be the electron will come, hole will come, they will recombine. When they recombine, the energy is given in terms of the light. This is called radiative recombination. Okay, so whenever there is a photogeneration, there is a radiative recombination. So that is balanced by so whenever there is a generation due to photon, there should be radiative recombination some other place. Okay, so they are balanced. Is it clear? So light fall generate electron and hole pair. Electron hole generate means recombine, they get light. Clear?
Yes.
Okay. Similarly, impact ionization means what? See, in this you see the electrons are generated, right? The electrons are generated, right? If they have some energy, right? If they have more energy, okay, they also can generate, right? They also can help in conduction. Okay. So what do you mean by impact ionization means? You know, the ionization is because of collision. Okay, so whenever electron and holes are generated, right? So this free electron and hole, they are moving in the crystal, right? So since they are moving in the crystal, sometimes they also will collide with the atom, and they'll give the energy to generate electron hole pair. Clear? Suppose this electron is having enough energy, some way it will move, may meet a silicon atom, and it may give the energy to the silicon atom to generate electron hole pair. Is it clear? This is called impact ionization. So the electron and hole pair after generation, they are moving freely in the semiconductor. They may meet some atom and give the energy to generate one electron hole pair. Clear? So the free electron and holes are moving in the semiconductor. They may meet some atom and give their energy. That is called impact ionization. Is it clear to all of you or not?
Clear, sir.
Yes.
So the reverse process is called auxiliary recombination. Okay, what is the meaning of this? Here electron have gone, hole have gone and impacted, giving the okay. So in impact ionization, what is happening? Electron is going, okay, and generating electron hole pair, right? I don't know. This generation, okay, right? And in recombination, what will happen? The electron will come and hole will come. Will come and they give the energy to another electron. Okay, so that is called other recombination. That is possible or not? See, electron and hole are moving around. Okay, they may the electron and hole pair are moving around. Okay, they are moving somewhere. Okay, they may meet at one point. Okay, here one electron will be there. They can give the energy to electron or not. Hello. Is it clear to or I need to explain you? What I am telling, whenever electron is liberated, right, they are moving around and they may hit a atom, generate electron and hole pair. Okay, and whenever electron hole pair is moving around, they may meet somewhere, they recombine and give the energy to another electron. That is possible or not possible?
Sure, sir.
So that is called other recombination. Okay, so in exam they will ask you A and B. Okay, then you have to combine, like they will give you 4 statements, you have to combine which one is correct. Okay, so there is another thing is called phonon. You know, phonon means the vibrating atom. Okay, if the electron hole pair is generated because of vibrating atom, that is called phonon ionization. Clear? I told you whenever atom vibrate, they generate elastic waves. Okay, if the generation is due to vibration atom, then that is called phonon or phonon ionization. Okay, and the corresponding is called phonon recombination. Okay, this thing may come in the exam. You have to balance which one is balancing which one. Clear?
Clear, sir.
Clear, na? Hello?
Clear, sir.
Yeah. So what I am telling, at a constant temperature, concentration remain constant. Okay, because for every generation there is a corresponding recombination. There is a balance. That is the statement I am making. Clear? Clear. One more thing, guys. Just before leaving the slide, I want to give you analogy. Okay, suppose you want to make the, see what happened, right? The electrons are generated. I will explain you. Okay, the electrons are generated. Okay, some other place it is recombined. Okay, you should not confuse ki if they are recombining, they are generating, how we are getting concentration. Suppose I want to give you one example. Okay, suppose in India you want to make the population constant. What you have to do? The number of people are dying should be equal to number of people taking birth. I don't know.
Right, sir.
Right. So at any point of time, if you want to make the population of India constant, you should ensure number of people taking birth is equal to number of people taking death. Okay, and it doesn't mean that the people who is taking birth is dying immediately. Okay, if people will take birth, he will enjoy the life, then he will die. Some other place people will die whose age is coming. Similarly, the electron and hole are generating, they have some lifetime. They will move around in the semiconductor. After the lifetime, then they will recombine. Okay, so that is the process. Not like they are generating, they are immediately they are dying. Okay, so like population, a person is taking bath somewhere, and some other place some person is dying. Okay, doesn't mean that the person who taken bath died immediately. Clear?
Clear, sir.
Yeah. So there is a lifetime. Like similarly, electron and holes also have some lifetime. We will study very clearly what is the lifetime of an electron and hole. Okay, so they will generate, they will stay sometime in the semiconductor, then they will die. Okay, this is the balance. Okay, guys. So now we understand that the electron and hole are generated. Okay, but have you thought like how the vacancy space helping you in conduction process? Right? So can anyone have any idea why this vacancy is helping you in conduction? Please tell me whatever things you are thinking in your mind. Right?
Free electrons occupy the valency and in turn creates another vacancy, and that get occupied by another free electron coming, and
Yeah.
that brings a connection process.
You are right partially, but not wholly. Can you tell me why you are not right completely? You said the key electron is occupying the vacancy. Like that you said.
The free electron is occupying a vacancy and then creating a hole again, vacancy.
How the electron is free, then how it is creating a hole? When electron is free, it is free, completely free, right? So you see this process. The electron is emanating, right? It is free to move anywhere, right? So when it meet a hole, how it will create another hole? Getting? I'm not getting. See what I'm telling. Tell you. Okay. Okay. See, so the electron is emanated. Okay. There is a vacancy. Clear? Now it is clear to you. Okay. And also here also some electron is emanated, and there is a vacancy. Okay. So now if this free electron will come and occupy this space, right? You will not get another hole, right? Like you are saying, suppose the electron will come and occupy here. Then how will you get a hole?
Initially, that electron created a hole as per the diagram on the top side. So,
yeah. There is a hole
so
here.
that hole will be occupied by another electron. And
that electron will not be free electron. If a free electron is coming and meeting, right? You're not getting another hole. Okay, so you are partial right. What will happen? Since this space is vacant, right? Since this is a vacant space, right? So I like that key. Another electron from bond, it will go and occupy the space. Okay, because it's vacant, right? Highly probable that another neighboring electron may come and occupy the space. So when this electron will go and occupy the space, this will be vacant, right? So I can say whenever a bonded electron go and occupy the space, I get another hole here, right? Similarly, suppose this electron will go and occupy this space here, then I will get another hole here, right? So the whole movement is because of bounded electron, not the free electron. Getting? So you can see the electrons are moving like this, and the hole is moving like this. Again, I am representing to confuse if you are confusing. There is a vacant space, right? Suppose this electron move from here to here and occupied. Okay, like this. So it's occupied means it's a see there is a hole here, right? Suppose electron go from here. When it go from here, you will get a hole here, right? And when it go and sit here, you will get an electron here. Clear? So electron moved like this, and the hole moved from here to here. Here also you see. Suppose this electron will move and occupy the space, you get another hole here. So electron moved like this, the hole was moving like this. Clear?
Clear, sir, clear.
Clear. So it is the movement of bounded electron that is giving the whole movement. It's actually the bounded electrons that are moving, not the hole. Right or not?
Right, sir.
Right. So let me tell you one more thing. Okay. Okay. So how the hole helping you in conduction? Okay. So already I have summarized you. Still I will tell you more clear picture. Suppose you take a semiconductor. Okay. And if you apply a voltage, right? And you know the concentration of electron in the semiconductor at T is equal to some temperature 300 K. Clear? So you know the concentration of electron, and from the concentration of electron you estimate the current should be I1, right? If I know the external voltage V, okay, is equal to V1, right? And if I know the electron concentration of the semiconductor, this is semiconductor, okay, I can know what should be the current, right? I equal to I1, right or not? Yes. Hello?
Right, right.
So what I'm telling, if I know the electron concentration, if I know the external voltage, I can understand how much current should flow. Hello? Hello?
Sir.
Yes. So suppose this is I equal to I1, you have estimated, okay? This is estimated. Okay? Clear? And you measure the current I2. Okay? So you take a multimeter, okay, and measure this current I2. Okay, and you will see this I2 will be more than the I1, which is estimated because of the electron concentration. Okay, getting what I'm telling? Hello? So you have assumed there is only electron present and estimated some current I1. When you measure the current I2, it is greater than I1. Okay, so there is a current because of something else, right? So if you take only electron concentration, if you estimate the current and if you measure the current, it will be more than what you estimated. Getting? Hello?
Yes, sir.
Yeah. So there is a current because of something else than only electron. Okay. That is called the movement of bounded electron. Okay. So here in semiconductor, like I mentioned here, apart from this free electron, right? This bounded electron also take part in the conduction. Okay. That is called hole movement. So even though the bounded electrons are moving, but for our visibility, for our understanding, we are saying the hole is moving. Clear?
Clear.
Clear. So suppose there are the number of holes equal to number of electrons in semiconductor, right or not? So, hello?
Sir, I have one doubt.
Please tell me.
In the same figure, you have shown that the movement of holes is like with the help of the bounded electrons.
Yeah.
So actually, how the free electrons are moving?
Free electrons are completely free. Okay. See, the electrons are
The direction of movement.
not under the influence of any atom here. Okay, they are free to move anywhere in the crystal. Okay, so if you apply a voltage, then they will move according to the field applied. So suppose they are now undirected. If there is no external bias, they are moving randomly. Okay, if you give a external bias, they will move in a particular direction. That is called electron transport. That we are going to discuss in the transport chapter.
Okay,
How?
okay, okay.
Okay, so the electron will be moving like very randomly, anything like this, randomly moving. Okay, but when we apply electric field, right, there we are pushing them to move in that direction.
Okay, right. Got the point, sir. Good.
Fine, so in this, and also I told you at equilibrium, no net motion, right? No net motion. So if you see in a particular cross section, the net motion will be 0. But if you apply a field, because of the external field, the field is directing the motion to a particular direction. That's why we are getting current. Okay, even though at t equal to 0 they are moving, we are not getting current because the motion is random. There is no net motion. When we apply external field, there is a net motion because of the external electric field are pushing the electron in a particular direction. Clear?
Clear, sir. Clear.
Clear. And also, since this vacancy space, right, in at equilibrium, the number of electrons is equal to number of holes. Okay, and the hole is nothing but vacancy space. So the vacancy space also helping you in conduction. It's not the hole helping you; it's the bounded movement, right? The electron, suppose the electron which are bounded, they are occupying the whole space. Okay, so this is the motion of bounded electron is helping you in conduction. Not so in otherwise, instead of telling you bounded electron, I'm telling you holes. Okay, because and the holes, if you see, are moving exactly opposite to the bounded electron movement, right or not?
So when these bounded electrons are moving, then number of bounded electrons are actually equal to the number of free electrons, right, sir?
No, number of holes equal to number of free electrons.
Okay, I think in the internal meaning.
See, in this you see, there are 2 electrons, right? And there are 2 electrons because their 2 bonds are broken, and I am having 2 holes only. Exact 2 holes I am having.
Okay.
So the electrons are moving somewhere, and I am having 2 holes. And because of 2 holes, suppose this electron is moving like this, okay, and occupied this space. I get another hole here. This hole is now completely filled. Now I get electron here, right? So electron move like this, hole move like this. So at any point of time, we have only 2 holes.
Okay. Okay.
Clear. But the thing is, it's not the vacancy space moving; it's the electron is moving. But for your clarity, for you giving a better understanding, that hole is introduced.
Okay. Okay.
Okay. So let me tell you one since you are asking more questions, I am giving you one more analogy. Okay, in this point. Okay. So the analogy is, suppose I have a tube completely full of liquid. Okay, completely full of liquid. If you tilt it like this, okay, you cannot see anything moving, right? Right or not?
Sir, what's the item? It's
So
not.
I'm telling this is a tube where I completely filled with liquid.
Tube. Okay. Okay. Fine, sir.
Tube with completely filled of liquid. Okay. So if you tilt it, can you see anything moving? No, no, because it is completely filled, right?
Yeah, it's filled.
Yeah.
Okay.
So suppose I take a second tube. Okay. So it's little bit vacant, otherwise it is filled. Okay. So now if you tilt it, what will happen? This vacant space will come like this or not? So this will come to like this, and this water will come like this. If you tilt it, what will happen? This bubble will come upward or not? and this will fill. Again, if you tilt more, what will happen? The bubble will come to here, and this will be filled. Right? So if I tilt it, again I am giving a picture. Okay. Okay. This is a bubble. Okay. Right? It is a bubble. Okay. Suppose I tilt it. What will happen to this bubble? It will come upward, na? Right? The bubble will move up, upward or not. Wait till it. So will this bubble move upward or not?
Yeah, sure, sir, sure.
So is there any confusion in this? So I'm telling, when I'm tilted it like this bubble will move upward.
Yeah, due to the water flowing there, seems like
Yeah.
bubble
So
moving upward.
first thing is, all of you are convinced that the bubble will move upward. If I tilt more, again the bubble will move upward. Clear?
Got the point, sir. Great analogy for that.
Yeah. So thing is, actually the hole is not moving. What happened? The water, when you tilt it, right? The water is coming and filling it up, so that the bubble is moving away. Right? So when you tilt again, what will happen? This water will coming like this, and this is creating a bubble. Okay. Actually, the water is coming downward, and the bubble is moving upward. Okay. Actually, the water is moving downward, but you are seeing like a bubble moving upward. Right or not?
Yes, sir. Yes, sir. Exactly.
So same thing happening. So it's your wish. It is convenient for us to look the bubble than the water moving downward. Right? So that's why we are seeing the bubble. Similarly, hole. So hole is for our convenience. So it is convenient to use the concept of hole to make us understanding better. But practically, the electron which are bounded, they are moving. Clear?
Clear, sir.
Okay. So all of you clear or not? Guys, please tell me. Is there any confusion in this?
Clear, sir.
Clear. Okay. So at t greater than 0, if t greater than 0, the current was less because we have neglected the movement of hole, nothing but movement of boundary electron. Okay. Clear? Yes.
Clear,
One more
sir.
thing I want to tell you. If you see, right? You see, the electrons are free to move like anything. Okay. But the bounded electrons, right, only can move to holes, right? So thing is, if you see, the movement of electron is easier than the boundary electron. Is it clear or not? So in this semiconductor, the electrons can move freely anywhere, right? So the movement of electrons are much more easier compared to the movement of boundary electron, right or not?
Right, right.
Right. So if I apply a potential, right? So since the movement of electrons are easier, right? They are easier to move, right? So if I apply electric field, even though the electric field force is same for electron and hole, so even though the electron and hole are getting the same force from the electric field, this is electric field, right? Electric field, okay. But since the electrons are easier to move, okay, the current due to them will be more compared to holes. Clear?
Clear, sir.
Clear. So since it is easy for the electron to move around the semiconductor compared to the movement of holes, if we apply external electric field, it is obvious the current due to electron will be more compared to the holes. Okay. So for encountering this one, we have introduced something called effective mass. What is effective mass? If you go to free space, right? Free space, the electron mass will be equal to hole mass. Okay. But inside the semiconductor, since for the same field, electron is moving better than the hole, so we are telling in a virtual way the mass of holes is little bit more compared to the mass of electron. This is called effective mass. This is not the actual mass. This is the mass inside the crystal which is introduced effective. This is effective mass in order to explain why the conduction of holes are like why the conduction of electrons are better than the conduction of holes. In order to explain that concept, we have introduced something called effective mass. Effective mass is nothing but mass of electron inside the semiconductor or mass of holes inside the semiconductor. They are not the actual mass. Suppose if I say effective mass of electron will be some constant times the mass of electron in the vacuum. Or if electron will come outside, okay, if you weight it is m0, inside the crystal it is k into m0, because when electron is moving, right, it is getting opposition from this electron, this atom or this hole. So okay, whenever it is moving, right, it is not completely free, right, it will come into influence of many atoms will vibrate, or electron will be vibrating, there is phonons, so it may encounter many things. Okay, so you cannot directly apply force is equal to mass into acceleration, because even the force is same, the acceleration is lesser because the effective mass is here, effective mass is more, so k is greater than 1. Okay, so the effective mass of electron inside the crystal is more. Okay, so the effective mass is nothing but a constant time the mass in vacuum. Okay, similarly here one mass of hole nothing but constant k2 times the mass in vacuum. Okay, so it is not the actual mass, it is introduced to explain the how the conduction is less. Okay, so if you see the effective mass of hole is more compared to effective mass of electrons. That's why in say mathematically I can say the current due to the holes are lesser compared to the current due to electron for the same electric field. Is it clear?
Clear, sir.
All of it is clear, na? Okay, effective mass is a tedious concept which is introduced for our understanding. Okay, means because otherwise you see, suppose let me extend you. Suppose I want to apply for this electron, right? For this electron, it is under the influence of this external electric field. Okay, this electron is under the influence of external electric field. But inside also there are many things, right? The atoms is vibrating, electron is repelling him, this hole may be attracting him. Okay, there are many things inside. Okay, so in order to take all the internal forces into account, we have introduced indirect way of effective mass, because it is very tedious to encounter everything it is undergoing inside. Okay, so effectively you are telling the mass is more. So the which will inside they include the effect of all the internal forces. Okay, so the effective mass and including all the internal forces. For our easy mathematics, what you can do directly, electric field is equal to directly effective mass into something you can put. Clear? So this is effective mass takes into account all the internal forces a carrier is encountering. Okay, clear?
Clear, sir.
Okay. Is there any doubt on the effective mass, guys? Guys, please let me know if you have any doubt, because in 5 minutes we have to complete. Okay. So guys, have you got board? Hello?
No, sir.
Not board, na?
Yes, sir. No, sir. No board.
Okay. So this is now you understand what is the hole, what is the electron, what do you mean by semiconductor in equilibrium, what do you mean by steady state, okay, what is the usefulness of this subject EDC, okay, and you understand what is effective mass, okay. So there may be some question which is false. MP greater than Mn, MP less than Mn, MP, Mn less than MP. Which one is right? Guys?
MP greater than
This is right,
P
right?
greater than M. A.
Yeah, this is because the movement of holes is difficult compared to the movement of electrons, right? That's the meaning. Okay, don't think that there is some mass is more. Mass is same only, but inside effectively it is more. Okay. Okay. So now actually 2 slides remaining. Okay, to complete this bond model. One model is over. Actually 2 slides only remaining. This band model is coming. Okay, so only 1 slide is remaining for the band model, bond model. Okay, then we will go to band model. So shall we continue or shall we stop? So and also I'm telling this is a very important slide. If you are little bit like tired, I can stop it here, because this is a very important slide. I don't want to move it faster.
It's okay for me. I don't know. Everyone is comfortable. It's okay.
because I need 5 minutes and I want your attention also. Okay, so better see, you just go through whatever things I have studied till now. So next class, whatever we have studied till now, we'll use this and get a qualitative model of the concentration at equilibrium. Okay, then you will go to band model. In band model, we will get explicitly what is the concentration. Okay, so if you see in band model, right, we will explicitly get what is the band concentration. Okay, so next class we will see complete the band model, also bond model. Okay, also since we have understand the basic of semiconductor. Okay, so we can go little faster in next class. We will complete the band model and also we will go to the extensive semiconductor. Okay, also just last but not the least, we just believe that even though we are going little slow, okay, but these concepts are very more important than others. Okay, if you see in the syllabus, right, so if this is very well understood, right, this part, okay, then this are very easier, we can go very fast also. Okay, so we have to give some time to this term. Suppose we have around 16 hours. Okay, so we'll give almost 6 hours to this one. Okay, then we'll give 2 hours to this one, 6 to 8. Then we'll give suppose 4 hours to PN junction and 4 hours to BJT. Is it clear? Right?
Clear.
Yeah. So we will try to give you a very basic understanding of physics. Okay, there are many things. So actually it's a very big subject. Okay, still I will try to give a capsule of what is the thing going on. Okay, and I will make sure you are visualizing the things, then just mugging up the things. Okay.
No, sir, visualizing only.
Okay, yeah. So I will ensure my best you are understanding each and everything from visualization. Means next time we don't need to mug up anything from the subject. Okay, that is my surety from my side. Okay, just stay attentive. I will ensure that it will be easy subject for you and you will not mug up anything in the exam. Okay, so that is my aim before teaching you. Okay, so guys, we shall stop here. So thank you for the person listening. See you in the next class. Okay, so good night all of you.
Thank you, sir. Good night.
Thank you, sir. Good night.
Good night.